Hello everyone. In the previous lecture, we had discussed a problem involving a nonlinear material. Uh, in this lecture, we are going to go back to linear material, but we are going to have uh, an enhanced discussion going beyond the purview or scope of strain energy due to just bending. Specifically, we are going to discuss a problem involving not just bending, but also uh, uh, torsion. Okay, so in preparation for that and slightly in a more expanded fashion, what we'll do is we'll first mention the strain energy due to bending, which we know. Okay, strain energy uh, for bending, something we already know. And please note that these pertain only to beams or rods. Uh, for uh, for axial stretching, what we'll have is integration 0 to L p square by twice AE dx, and for torsion, the strain energy due to torsion, for that we are going to have integration 0 to L p square by twice Gj, where J is the polar moment of inertia. And here of course you note that this A is the cross-sectional area of the beam or rod under concern, and this G here is the shear modulus, this J is the polar moment of inertia. Okay, now unlike this formula for the strain energy due to bending, which I had derived in a previous lecture, I am not going to derive the strain energy due to axial stretching or the strain energy due to torsion. I expect that you will be able to do it in just the same fashion that we had done it for this case. Uh, for students enrolled in this course, we can, if you try and you find some difficulty, we can of course have a discussion during one of our live sessions. All right, now let us look at an application of this. Uh, so we consider uh, we consider a, uh, a structure like this. Uh, so this is our wall here, and we have a thin rod extending like this out of it, but it doesn't end here. Rather, it is in this form. Okay, so this is a very thin structure. So both these parts are very thin. Uh, this length um, so this length is L1. This length is L2, and uh, we have this entire structure loaded by a force which is like this. Let me redraw that. This is the force P, the point force P acting at this end. So very quickly you note that, and we will go into the details of the calculation. Uh, if you look at this, you will immediately realize that surely due to this applied force P, there is going to be bending induced in this structure. There is no doubt about it. We are all familiar with it. But alongside that, we are also going to have a torsion applied on this horizontal part of the structure. Okay, because you can understand that this force P, it is going to have this momentum L1, and that PL1 will act like a torsion It will act like a torsion at this end over this structure. Okay, so uh, and you can have more complicated structures where in addition to this bending and torsion you may have stretching also, but in this problem we are not going to have any stretching involved. Okay, so let us see how we can address this problem. Okay, so uh, what we are going to do is we are going to address this problem part by part. So let me name these things, name these different points. So this is A, this is B, this is C. So first of all, uh, for the part, let me draw it here. So for the part AB, okay. So for the part AB, what I'm going to do is to take a cut section at a distance. Draw that slightly better. Okay, let me take a cut section like this at a distance S1 from this end. Okay, so this is S1. And now if I take the free body diagram of this, you understand that this has very much a circular cross section. Uh, so I have this force P acting at this end. This is the exposed section as a result of this cut section, and you understand that there is going to be a shear force and a bending moment present here. So let's say this is our shear force, and uh, and this is our bending moment. Okay, so it is very important that you have a clear three-dimensional visualization of this scenario. Now, what is this M? This M is simply given by this equation. We have seen the application of or how it comes about in our previous discussions. Uh, but just to clarify, this distance is S1, which acts as the moment arm for this force P, and this is well, in this three-dimensional picture it doesn't make any sense to talk about the clockwise and the counterclockwise sense, but you understand that the sense of the moment contributed by this force P about an axis which passes through this end will be opposite to the sense of this bending moment M, which is represented by this capital M, which is why for the moment PS1 we have this minus sign over here. So overall this is just M is equal to PS1. Okay, and that's it. So for the part AB we do not have to discuss anything more, because you understand that our whole idea is to take these the cut sections over these different parts, and then at the end to write the entire strain energy contributed due to the bending, due to the torsion, everything together. And finally, once we have that, or once we have the expression for that strain energy, we can simply go ahead and utilize the Castigliano's theorem on deflections to find out the deflection. Okay, so by the way, since I have not explicitly mentioned it, our objective here, as always, is to find out the deflection at this end A. Okay, so let me perhaps write that down clearly. So what is the deflection at A? That is our question. Okay, that is what we are trying to answer. Okay, for these kinds of problems, of course, it is very much possible to extend our ideas from the previous lectures and to ask that what is the deflection maybe at the point B, or even at the midpoint between B and C, in which case of course we have to apply a fictitious force at that point and then proceed just like as we had done before. Of course that will involve a bit more algebra. Nevertheless, we'll proceed with our question here, which is to find the deflection at A. And next what we are going to do is discuss what happens for the part B. Okay, so for the part BC rather. Uh, so what I'll do is set this question maybe here, so it is not confusing with what I'm going to write now. Uh, so for the part now, this is where it gets really interesting. So for the part BC, what we'll do is we'll take a cut section uh, maybe somewhere here, but before that what we'll do is we will since we have said for the part BC, what we'll do is we'll actually isolate out this part BC. Okay, but so when we say that we'll isolate this part BC, what we basically mean is that we are taking effectively a cut section at B. Okay, so what is the implication of that? Let's see. If we indeed consider it like this, if you're removing the part AB in our thought, then okay, so this is the exposed section as a result of the cut at B. What we effectively need to do is we have to incorporate the effect that this force P uh, that what it would have at the point B in this diagram. Otherwise, this diagram what we are drawing is incomplete. Okay, so let me complete this thing. That's my wall. No problem about that. Okay, so basically I've removed the part AB, and now I have to pay a penalty for artificially removing that part AB by having to incorporate the influence of the force P. Now, what is the influence of the force P? That is the big question. First of all, you note that since I'm removing the part AB, what happens to the part AB itself? Okay, once I remove that, okay, so I'm considering these two things in isolation. Okay, so this is my force P. Now to balance this force, I must have a shear force acting on this side. Okay. Now that shear force conventionally I could write like I have done it here, but that if you write that as V, that V is going to be equal to minus P. So I'll just immediately write that thing. I'll directly write that thing, okay, in this fashion, that this is my P. Okay, so if you understand that if you write it in the form of a shear force and you direct the shear force in the other direction, that V is going to be equal to minus P. So it all depends how you choose your local coordinate system. So so like this S1 is along the AB, what is in which direction you are taking the axis transverse to this AB. If you take it in this direction, then P is positive along that, then that V is going to be equal to minus P. However, if you take the transverse direction coordinate axis in this direction itself, then V is of course going to be equal to P. Okay, so you understand what is going on here. But very importantly, from the mechanics point of view, this is not the end of it. It is not the end of it because you understand that there will be a moment also. Okay, so so that moment here is going to be equal to PL1. Okay, So it directly follows from here. So we can write that. Okay. Now what about this part? Okay. First of all, you note that this force E that is acting in this direction, it will have a counterpart on this cross section. Okay, and that will be directed in the opposite sense. So it is like that. So this much is easy to understand. Next, what is the influence of this P over here? It is again this PL, but you note that this sorry PL1, but this PL1 is not like a bending moment for this part BC. Rather, it is, just clarify this thing. This is the entire part AB I am considering, and this is the entire part BC I am considering. Okay. So the PL1 that is going to be applied here, that is going to be applied in the form of a torsion. Okay. And the sense of that, of course, is going to be in this other way around. So let me just draw that. This is PL1. Okay, now I've made a big deal of talking about the sense of these directions in a rather formal fashion, but even without doing this, I mean, even intuitively, okay, although I strongly advise that you do not proceed for these mechanics problems intuitively, but just as a source of satisfaction, you can note that this force P, it is of course going to exert a torsion in this sense, okay, going in this sense. Okay, so if you're looking into the part BC, that is in the counterclockwise sense or the anti-clockwise sense, which is what this PL1 is indeed turning out to be, as we have just discussed in a different way. Okay, now our job is only half done here. Okay, as far as understanding the forces, the torsion, and the moments are concerned here, because when we were considering the part AB, we had taken a cut section at a distance S1 from this end, and that job is still not done. So we have to take a cut section uh, at a certain distance from B and consider that over that portion which is exposed by the cut, uh, what is going on there. Okay, so we take a cut section at a distance S2. So this distance is S2 from the end B, so that what we are really dealing with here is this part, which I draw in a slightly bigger way. So I do have this force. Maybe I should. Okay, so I have this force P, which is just this force P. I have this torsion or this torque acting at this end B, but at this end, which is the exposed surface due to this cut section here. So this distance again, mind you, is S2. At that end, what I will have is a bending moment acting in this plane. Okay, so suppose if I were to write uh, my uh, my x-axis in this fashion, my uh, my y-axis in this fashion, and my z-axis in this fashion, then for this bending moment which I have just drawn, that bending moment is actually lying in the plane xz. I repeat, this bending moment is lying in the plane xz. And please note that this torsion, its sense is along the x direction. Okay, so if you curl your finger along this arrow, then your thumb would be pointing in the positive x direction. Okay, and this one, that is so if you curl your finger again uh, along this arrow, then your thumb would be pointing in the negative y direction. Okay, so actually this is much easier to discuss uh, in a face-to-face discussion, uh, but I really hope it will be clear. Okay, so because I have just mentioned the direction in which your thumb should be pointing, so again I repeat, if you curl your finger along this arrow, your thumb would be pointing in the negative y direction. All right, now let us write down the equation for the bending moment. So for this m, okay, now for this m, it will be m minus ps2 equal to 0. So this is just m equal to ps2, and t, the torque, simply pl1. Okay, so for the part AB, we have no contribution from the torsion, we have only the contribution from the bending, which is m at a generic distance s1, it is m equal to ps1. And for the part BC, at a generic distance s2 from the part B, from the end, from this point B, we have m equal to ps2 and we have t equal to pl1. Okay, you note that I mean there would be a compensating torsion at this end. It is that what we are talking about. Okay, so plus you also note that, I mean, this diagram is far from complete. You would have very much a shear force in that direction. So if you draw that, shear force, that V is going to be equal to minus P, and uh, you can actually draw a compensating torsion here, but I will just refrain from doing that because it has already cluttered up the picture over here. Okay, so maybe over here. Okay, so this is our T, so that T is this T. We have the V also. This V is going to be equal to minus P, but we won't need it anyway. uh, uh, on that note, I mean, you could have strain energy associated with shear, but here, but usually that contribution is very small. We are not going to get into that discussion, but it is possible to have the strain energy associated with shear also. But in all these problems, we are neglecting that contribution. Okay, so now it is time to account for these different parts altogether in the expression of the strain energy, and that's exactly what we're going to do in the next page. So for our total strain energy, we have from 0 to L1. So this is 0 to L1 corresponds to the part AB. Here we have the contribution solely due to bending, which is why we write the strain energy associated with bending. For the part BC, we have to carry out the integration from 0 to L by L2, and there we have the contribution from the bending, which is again m square by twice EI, plus we have the contribution from the torsion, which is t square by twice GJ. This entire thing, I've made a mistake here. This integration is actually with respect to ds1, okay, with respect to the s1 variable. And just to make things very clear, this is for AB, and this is for BC. Okay, so now if you try to find out the deflection at the point A, all that you have to do is carry out this differentiation of the total strain energy U with respect to the force P, which is applied at the point A, and what you are going to end up with. So let me just write one intermediate step. So this is just as before, m by EI del m del P ds1 plus integration 0 to L2 m by EI del m del P ds2 plus integration 0 to L2 T by Gj del T del P ds2. And I'm not going to go through the intermediate algebra. You can all do that. So the ultimate answer that I will obtain is PL1 cube PEI plus please note that I am not doing some trick here to directly obtain the formula. I have actually skipped some steps. I have the answer written down on a piece of paper near me. I'm just looking at it and writing down the answer. Okay, so there is no magic involved. You actually have to do the intermediate steps to get to this answer. Okay, so that's it. Let me just check. Yeah, that seems correct. Right. Okay. You can have, as I mentioned, you can have more complicated structures. You could have variations on this problem where maybe you are asked to find out the deflection at some other point, in which case you have to apply a fictitious force here, carry out this kind of a differentiation, and ultimately set that fictitious force value to be equal to 0. So you can have very many different kinds of interesting variations on this kind of problem. All right. So on that note, I'll end this video lecture. Thank you.